All right, welcome everyone. Your NIOS board exams are coming up, so today we're tackling a big one, electric charge and fields. My goal here is simple, get you prepped and ready for that exam. So let's just dive right in.
Okay, so here's the game plan. We're going to start with the basics, what is charge? Then we'll get into how they push and pull on each other with forces. After that, we'll explore this amazing idea of the electric field, which is how they do that without touching. We'll check out a special case called a dipole, and then I'll show you a super useful shortcut called Gauss's law. And of course, we'll finish up with a super fast recap of everything you need to know.
All right, first up, we gotta start with the absolute basics. Let's get a real solid handle on the thing that pretty much powers our entire world, electric charge. So where we're starting our journey is in a place called electrostatics. And honestly, you can just think of it like a freeze frame for electricity. We're looking at charges that are just sitting still, not zipping around in a current. And understanding them when they're at rest, that's the foundation for everything else.
So, when it comes to charge, there are only two flavors, positive and negative. Super simple. And we can thank Benjamin Franklin for that convention. It's kind of cool how it works in real life. If you take a glass rod and rub it with silk, electrons literally jump from the rod to the silk. That leaves the rod with fewer electrons, so we call it positive. Now, do the opposite with a rubber rod and some fur, the electrons jump onto the rod, giving it an excess, which we call negative. So the big takeaway here, and this is super important, is that we're not creating charge out of thin air. We're just moving those tiny electrons around.
Okay, now for the three golden rules of charge. You gotta know these. First up, attraction and repulsion. You've heard this a million times, opposites attract, likes repel. Easy. Second, conservation. This is huge. You can't just make charge or destroy it. It only gets moved around. And third, this one sounds fancy, but it's not. Quantization. All it means is that charge comes in tiny, discrete packets. The smallest possible bit of charge is the charge of a single electron, which we call E. So you can have 1 E, 2 E's, a billion E's, but you can never, ever have like half an E. It just doesn't work that way. These three rules, they are the absolute bedrock of everything we're about to talk about.
Okay, so we know charges push and pull on each other. But how hard? I mean, physics is all about being precise, right? We need to be able to calculate that force exactly. And luckily for us, there's a fantastic formula for that.
And that brings us to Coulomb's law. This thing is an absolute cornerstone of electrostatics. It's actually pretty simple. It tells us two main things. First, the bigger the charges, the stronger the force. Makes sense. But second, and this is the really cool part, the force gets weaker the farther apart they are. But not just weaker, it drops off with the square of the distance. So if you double the distance, the force doesn't get half as strong, it gets 4 times weaker. That's a huge drop. This whole inverse square thing pops up all over physics, so it's a good one to remember. So let's actually look at the formula itself. You've got the force, F, and it equals some constant K times the two charges, Q1 and Q2, all divided by the distance squared, R squared. Now that K is just a number to make all the math work out. But what's really amazing is if you squint at this equation, it looks almost exactly like Newton's law of gravity. I mean, seriously, one is for masses, this one is for charges, but the structure is the same. It's a beautiful bit of symmetry in how the universe works.
And speaking of that constant K, get this. Its value is 9 times 10 to the 9th. That's 9 billion. It's a massive number. And what that tells you is something really profound. The electric force is ridiculously strong. I mean, on the scale of atoms and molecules, it completely crushes gravity. It's not even a contest.
All right, so there's this force. But wait a minute. How does one charge over here even know there's another charge way over there to push on? They're not touching. How does that force travel across totally empty space? This puzzle, what physicists called action at a distance, it leads us to our next really, really big idea.
I mean, that's the million-dollar question, right? It's not magic, so there has to be a mechanism. How does a charge here reach out and affect a charge over there? Solving that puzzle gave us one of the most powerful concepts in all of physics.
And the answer is just brilliant, the electric field. So get this, instead of thinking about one charge pulling directly on another, imagine that a charge actually changes the very fabric of space around itself. It creates this invisible field of influence. A great way to picture it is like putting a bowling ball on a trampoline. It creates a curve, a dip in the fabric. Any little marble that rolls nearby will get pulled into that curve. Well, the electric field is that dip in space created by a charge. And we measure how strong it is, E, by just popping a tiny positive test charge in there and seeing how much force it feels. Now, we can't see these fields, but we can draw them. We use these things called electric field lines, and the rule is simple. For a positive charge, the field lines just shoot straight out, radially, in all directions, kind of like rays of light from the sun. These lines show you exactly which way a positive charge would get pushed.
And for a negative charge, you guessed it, it's the complete opposite. All the field lines point inward, towards the charge. They show the direction a positive charge would get pulled. So a key rule to remember is that field lines always point away from positive and towards negative.
Okay, so we've got a handle on single charges. Now let's look at something super common and really important, something you are almost guaranteed to see on your NIOS exam, the electric dipole.
So what is a dipole? It's really simple. It's just a team-up of two charges, one positive, one negative, with the exact same strength, separated by a tiny little distance. A perfect example is a water molecule, and we measure how strong this dipole is with something called the dipole moment, P. All that is the size of the charge times the distance between them. That's it!
Now, because you've got two charges, the electric field gets a bit more interesting. And for your exam, there are two special spots you have to know. The first is called the end-on position. That's anywhere on the line that goes right through the two charges. The field there is pretty strong. The second spot is the broad-on position, which is on the line that cuts right through the middle, perpendicular to them. And here's the kicker. The field here is only half as strong as at the end-on spot, and it points the other way. Knowing that difference, that's a classic exam question.
So imagine trying to use Coulomb's law to figure out the electric field from, like, a giant sheet covered in charge. You'd have to add up the force from every single charge. It would be a total nightmare. But don't worry, physics has given us a beautiful, elegant shortcut for situations like this.
Okay, before we get to the shortcut, we need one more new idea, electric flux. And it sounds complicated, but just think of it this way. It's a way of counting how many electric field lines are passing through a surface. Imagine holding up a hula hoop in the rain. The amount of rain passing through the hoop is the flux. So more field lines poking through an area, that just means you have more flux.
And that brings us to the big shortcut, Gauss's law. This law is seriously cool. It says that if you imagine drawing a closed surface, like a bubble, around some charges, the total electric flux coming out of that bubble depends only on the total charge you've trapped inside. It's wild. It doesn't matter where the charges are inside the bubble or how they're arranged, just the total amount. And this simple, amazing idea makes it super easy to calculate the electric field for things with nice symmetry, like a sphere or a long cable, problems that would be a huge headache otherwise.
Whew, okay, that was a lot. So let's boil it all down. This next part is your quick and dirty recap of the absolute must-know stuff for the NIS exam. This is your core cheat sheet right here.
Okay, here it is, the whole story on one slide. It all starts with Coulomb's law, right? That gives us the force. But what causes the force? That's the electric field. Now, if you arrange those charges in a special way, you get a dipole moment. And finally, if you want a clever way to figure out the field from the charge, you use Gauss's law. See how they all connect? You nail the links between these four concepts, and you've basically nailed electrostatics. So, as you finish up studying for the exam, I want to leave you with one last thought. We've talked about forces and fields and flux, but what's the one big idea that ties them all together? It's the electric field. That's the star of the show. It's this invisible thing that fills all of space. It's what creates the force. It's what we measure with flux. If you can really wrap your head around the concept of the field, everything else just falls into place. Okay, that's it for me. Now go ace that exam.